So when we start looking at free radicals here, all right, the first thing we want to talk about is heterolytic and homolytic cleavage. The breaking of a covalent bond either being equally split, you get your electron back that you brought to the covalent bond and I get my electron back, or one side gets both electrons and the other one is short. If one side gets all the electrons in the bond and the other side doesn't, we call that heterolytic, and they call it fission here, or heterolytic cleavage. This is normally what we see when a polar covalent compound that's soluble in water is placed into water. We're talking our acids here, really. We place our acids into water and they donate that proton to create hydronium. Well, that's a breakdown of the bond between the anion and the hydrogen, where the hydrogen loses both, loses its own electron, but uses the electrons that are in the bond, and one side becomes positive and one side becomes negative. That's what happens when I place something into a solution. But what if I have HCl as a gas, okay, and it also breaks? Well, what could happen is what's down here on the bottom, something called homolytic cleavage, where one side gets one electron, the other side gets the other electron, and what we've created is something known as a radical. And the reason it's a radical, or a radical's definition, is I have a lone rogue electron that doesn't have a partner. Remember, I rather be how I am on the periodic table, how I appear in nature, and this is why Cl is Cl2 and H is H2. I rather appear like that, or I rather be bonded and have that happy magic 8 noble gas configuration. If I break like this, where each side gets one electron, these guys, or girls, I don't know the sex of our radicals here, but they're going to go hunting for another electron. So there's less energy demand for homolytic fission, homolytic, essentially, cleavage, but I create two very reactive molecules or atoms out of the situation that are going to go and look for electrons on things, electron-rich things, to essentially achieve that stability of the magic happy 8. The reason this happens up here is due to the fact that water, and this is what it says here, driven by the energy of solvation, water allows this to happen. Water's ability to do hydrogen bonding, water's ability to dissolve things is what causes the heterolytic cleavage. It's more energy than doing this way, because one side has to get the electrons, the other side loses out on the electrons, and then the water stabilizes these compounds. This is a lot easier to achieve, but they become radicals. They become electron hunters, electrophiles, if you will. Okay. So how could we make these? Well, we can make them by heat, or we could also break the bond using light energy. Okay, so that you could use heat, thermolysis, or you can use photolysis, light energy. Okay. So here's the different energy amounts for different colors lights, red, blue, and UV light. Okay. UV light can decompose a lot of organic compounds. it has a strong enough amount of energy that goes with it. And what we're looking at here is, well, we have the wavelength, and we have to go back to our Gen Chem. And if I have wavelength, then I have to have a frequency, and then E equals h nu. All right, where Planck's constant is h, and we multiply that by the frequency to figure out how many joules, and so on. So UV light has enough energy to break things down. Here's some changes in energy of our, chlorine, bromine, iodine that would be required to make the radicals. So I would need to put in 151 kilojoules per mole. This is the Gibbs free energy again, 243, 192. So if we just look at it, blue light could be enough to break up chlorine, bromine, iodine, putting in those sources. This is why we don't like using iodine as our alkyl halide, because when the iodine gets attached, it's very easily to break down and become unstable. Okay, so thermolysis, that needs heat. However, photolysis, I could make my radicals, but do them at room temperature. Because the light energy is enough energy to bring in that I don't have to ramp up my temperature. And why that's important is, well, what if I have a compound that I'm looking to turn into a free radical, but at higher temperatures it becomes unstable, or it becomes it's volatile or flammable, or whatever you want to say, and I still want to make the free radicals? Well, I could just expose them to light. This is also an idea of UV light and people studying. I know there's an epidemiologist up at Keystone that was studying the effects of tanning beds on natural flora of the skin, looking at exposing Staph aureus and things like that to UV light over long periods of time and seeing what happens to them. Because essentially the UV light is going to break down the biological compounds, since our biological compounds are organic compounds. So here's a typical photochemical reaction. We got two phenyl groups. We got a ketone here. And H nu, there's Planck's formula, that represents light. You see that over an arrow, that represents that you are giving it light to have the reaction go. Okay. We could end up with free radicals during the product after being exposed through a few steps. I am not going to expect you to know the mechanism or anything like that for this. What you should know is that there's homolytic cleavage and heterolytic cleavage, that the heterolytic cleavage is less energy, the heterolytic cleavage is more energy, the homolytic cleavage is less energy, it can be done by heat or light, but it creates free radicals. Okay. Azo compounds love to do this. We talked about azo compounds in our last chapter. All right, if we have an azo compound and we apply heat to it, we can end up with free radicals. So if I break down I make my azo dye and I heat that dye, I could then create a free radical situation. And here they're showing you where the free radical, that electron can move around, make a double bond, end up over here on nitrogen. Up here we got peroxides, work very well at doing this. So free radicals are seen in our organic chemistry a lot. And a lot of the compounds that we've talked about through the semester and I guess 3/4 we're at now can be seen here. check this out. So here's an organometallic initiator, and Grignard is an organometallic compound also. Okay, we're not going to really get into organometallics, but Grignard is an important one that we see a lot, and there's Grignard again. That's why I kind of brought it up again today. I meant to bring it up, like I said, with alcohols, but kept forgetting to, and then, reviewing for today, I was like, oh, I better talk about Grignard first. Okay. So the formation of our Grignard reagent actually is free radicals forming and then bonding together to make our Grignard reagent. So right here, the phenyl MgBr is our Grignard reagent that we talked about at the beginning of our lesson today. So what happens is the magnesium gets attracted to the bromine. The bromine's electrons come out, and the bromine, is hanging out there and bonds to the magnesium. But the magnesium is looking to make two bonds. Bromine can only bring one space for magnesium. So magnesium, not happy, looking for a partner. The phenyl group took a electron back with it. It's looking for a partner. And that's how this compound is made. This one's pretty cool up here. Where I could actually, with heat, take this compound and remove the methyl groups as 4 individual radicals. Okay, here's another one that's an electrochemical reaction, where you're actually doing a redox reaction in theory. Okay. And creating a totally new alkyl system, getting rid of the acyl carbons as CO2, or the acyl carbon and the oxygen, I should say, as CO2. Okay. So I've got an alkyl halide. SET stands for single electron transfer reactions, where only one electron is being transferred. Okay. In one of these reactions, we end up with a free radical. The one electron that's being transferred goes to the halogen and makes the halogen negatively charged and happy. The alkyl chain is left out. Of the fun. And given the free radical. So the alkyl chain doesn't get an electron to replace the one that the halogen is taking away. I'm happy right now because carbon has the extra electron to bond to the halogen. The carbon takes its electron back, the halogen takes its back, but the halogen picks up the extra electron that's being set up in the reaction from some metal, something, and it becomes negatively charged while the carbon's left hanging, holding its electron and no longer has a partner. So the example they show you is this compound here. And again, all of this is noise over here. And what I mean by noise, all of this nitrogen, CH3, that doesn't matter. Okay, remember when we talk about these reactions, focus on where the leaving group is going to be. Focus on the carbon that's going to become the free radical. So what happens is you bring in a group 1 metal, because we're talking about a single electron transfer, a group 1 metal or a transition that has a +1. But usually a group 1 metal like sodium or potassium is used. the sodium donates its electron, becomes positively charged. It donates it to this bromine. Bromine takes an electron, its electron away. The other carbon that's attached to it takes its other electron or its own electron back. Usually it's represented by half arrows, guys, not full arrows, since both electrons aren't going. They usually use like a half arrow to show that carbon's getting its electron back and we're splitting half. We're doing homolytic cleavage. So a free electron is floating around from sodium. Bromine picks it up. Now, in reality, this Br minus, we really make sodium bromide. And we end up with a free radical sitting here. Okay, so if I see a reaction of an alkyl halide, okay, or some sort of carbon halide with, let's say, just sodium, and it shows sodium going to sodium positive in some solution. Here they choose ammonia. Okay, so if I see a solution and let's say a group 1 metal underneath, this is the reaction that's going to happen. A free radical, and my halogen is going to be negatively charged. The mechanism is straightforward. Bromine takes its electron, carbon takes its electron. I mean, this is not the full mechanism. This is the general what's going on. Bromine takes half of an electron, carbon takes the other half. Bromine picks up the electron that sodium is donating, and we end up with the free radical on the carbon chain. Again, as organic chemists, are we really worried about this? No, we're worried about this. So if you remember, whatever's attached to the halogen becomes the free radical, then you're set. Now, before you ask, yes, that free radical could move around if I have pi electrons that are constantly moving and I have resonance. The free radical could move around the structure, the ring structure. Okay. Questions on that? So there's another reaction known as Fenton's reaction that uses hydrogen peroxides, or uses peroxides in general, in the presence of iron 2. Usually iron 2 chloride or something like that, but the anion isn't important. It's the iron 2 that's important. But what'll happen is I'll create a hydroxide and this OH radical. Okay? It could happen down here just like so. Same thing if it's not an H there, but I have, a peroxide with a carbon group on it, same thing. I'll always form a hydroxide, and then the other oxygen will always be the radical. The thing that's important about all the radicals we looked at so far is what this sentence says at the bottom. They're very reactive, number one. And since they're very reactive, they don't hang around for a long time. They pick up electrons pretty quick, so they're short-lived. And what they're saying here, they're essentially less than 10 to the negative third seconds that they sit there. So manipulating these compounds and getting these radicals are very useful if we're doing a chemical synthesis reaction. So what about the stability and steric hindrance and all of this fun stuff? Okay. Well, here is silver being, so again, another, it's not a group 1, but it's a +1 that's going to sit there and take that chlorine away and make that free radical. Now, what's cool about this, and I know you're looking at this and like, holy crap, what the hell's going on here? If I make 2 moles of this, both being free radicals, they could link together. So here is this compound right here, and here it is again over here, and they're linked here because we created 2 free radicals. So essentially, it's this compound twice, this compound twice, triphenyl methyl radical, bonded twice to create this structure, which was created in the early 1900s. Well, it says 1900 right here. That's what was proposed, what it looked like. When this reaction was carried out and technology got better in the 70s, they did an NMR of this product. And they actually found it looked like this down here and not this, because that the lone radical was stabilized throughout the ring by the pi electrons in the phenyl groups. And what they found out is that actually the steric hindrance of trying to bring these together played a more important role than even the stability of the benzene ring. So that's why the benzene ring, okay, with the pi electrons, or I should say the phenyl groups, because they're not benzenes in this case, but the phenyl groups, we lose that 6 electrons in the phenyl group and bring this out here. And the reason being is, well, this radical really wants to bond. If I leave that radical in here, okay, if I leave that radical in here, I've got a lot of steric hindrance. Yes, I've got resonance stability. I've got the 6 pi electrons moving around the phenyl ring. Everything's great. But for this to happen, look at all the steric hindrance we're going to have. Look how close these are together down here. Look at this up here. All right? Probably not going to bond like that, even though that's what the original structure was thought of, because it looked at it and said, well, we got to keep the stability of our phenyl groups together. And like I said, when they did NMR, here's what they found. Well, the reason being is that radical really wants to bond, and look, by bringing it up here and getting rid of the resonance stability in the ring to bring it up here, now that free radical is available with less steric hindrance. It's not stuck in the middle of big bulky phenyl groups, and now could freely bond. And that's what happens here. It freely bonds with one of these. So this product here is actually these 2 products added together. All right, here is this one here, and this is that one there. This has way too much steric hindrance, even though we have resonance stability. It doesn't even happen. There's too much steric hindrance there, and the steric hindrance takes precedent over the resonance stability of the phenyl rings. So this bottom picture is the one you see the most. Or all, I mean, I should say, is the one you see. I should say it that way. Good question, though. Some of these radicals that we can create, as we're seeing here in this slide, are very stable compounds. They're so stable that their half-life, as it says in here, are years, which means you could put them in a container and store them just as you would store any other, sodium chloride or anything like that, for that matter. They don't react with air, they don't react with light, and they are often very, very colorful compounds. We don't have to worry about traps and all of that. And let me see where I'm at here. Discard. I'm on 12. Okay. And I've been going for 50 minutes. All right. So I'm going to stop there. And here's the deal. That's me, by the way. The deal is this. You don't have class on Monday. All right, you guys don't have class on Monday because it's Easter Monday and they said we have to stick to that schedule. What I can also tell you is that finals will stick to the final schedule. So whatever time our final was supposed to be on in the classroom will be our final time on Blackboard. Now I'm going to finish radicals and that on Wednesday then, since we can't meet on Monday. Okay, so Monday there's no class. And then we'll have our third exam, right? It would be our third exam, I believe. And then whatever biochem I finish from April into May is what'll be on the final. Okay. Do you guys have any questions? Yeah, so the next exam, Sarah, will be free radicals, amines, and carboxylic acid. Yeah, you can. Carbon to carbon chunks will break up whether they're ring or not.